Today's topic is iron carbon phase diagram. This is the second part of phase diagram. Now, before starting iron carbon diagram, we have to know what is the allotropes of the irons. It has mainly three allotropes in solid condition, that is alpha iron, gamma iron and delta iron, which are BCC, FCC and BCC respectively at different temperature you can see. And also remember that up to 770 degree centigrade it is ferromagnetic in nature, and after that it is paramagnetic. And also you know already that in with different crystallography structure this iron behaves differently. Okay, that's why we have to study the phase diagram, because with mixing of carbon atoms the iron also behaves differently. Okay, let's start. There are different kind of allotropes. Those are α-Ferrite, gamma-Ferrite and delta-Ferrite. The temperature ranges are given here. That is up to 912 degree it is α-Ferrite, up to 900 to 1400 it is gamma or austenite, and above 1400 up to 1538, because after 1538 degree pure iron actually in liquid, this is delta-Ferrite, and they all form solid solution with carbon. The maximum amount of carbons that can be make solid solution, those are 0.02%, 2% or 0.15%, and those structures are like this. Okay, these are the solid solution. You can also see in my last lecture. Here is the carbon atoms. Okay, carbon atoms are actually guessed in this crystal structure, you can see. Okay, as carbon atoms are so small they can enter into the crystal structure. But what happens when they make a chemical composition with iron? This is actually intermetallic compound, and this is known as cementite, that is Fe3C, that ranges 2% to 6.67%, and its shape is orthorhombic. Okay, and now we can study iron carbon diagram. We already know the basic structure of iron. Those are delta-Ferrite, gamma-Ferrite, austenite, alpha-Ferrite and Fe3C, that is known as cementite. Now you can see these are the complicated lines. Now study one by one. First, look at this point, 1538 degree centigrade. Above this pure iron become liquid, but with increase of carbon composition at this direction we can see the carbon composition gradually increasing up to 6.7%. The melting point of iron, or better to say iron carbon alloy, decreasing up to a certain percentage, that is 4.3% of carbon. Okay, now what happened after that? You can see this line is dotted line. Okay, and others are continuous line. Why? Because all these lines are the symbolic of to show a reversible reaction, but this is not a reversible reaction. Okay, that's why we are using dotted line in the phase diagram. Okay, now what happened after 1400 degree? It is delta. This region is delta-Ferrite. This region is actually delta plus liquid. Okay, delta plus liquid. After that, this region is gamma austenite. Okay, this region is gamma plus liquid. This region is gamma plus cementite. This narrow region is alpha-Ferrite, which is most important. Okay, because all the iron alloy we are using these days, these are generally 0.2% generally. Okay, this is alpha plus gamma. These are here is alpha plus Fe3C. Okay, now what is the steel? If anybody asks you how much percent carbon is present in steel, that is 2.12%. Okay, and up to this percentage is known as hypoeutectic. Up to this percent, this is hypereutectic. Up to this is hypoeutectic. cast iron, and then it is hyper eutectic cast iron. Above 2.14% of carbon is present in iron carbon alloy, then it is known as cast iron. Okay, and if at carbon percentage is below 2.14%, that means it is known as steel. Okay, now see these names ACM, AC1, AC3. What are these? This is actually AC3 line, this is ACM line, this horizontal line is AC1 lines, and every lines have some significance. What are the significance? Above AC3 lines, after AC3 lines, carbon percentage increasing in gamma region. What happened actually? After AC3, that means after this line, you can see there is alpha and gamma is present. That means either carbon will shift to alpha region or shift to gamma region, because both crystal structure can carry a carbon atom. And what it say? After AC3 line, carbon percentage increase in gamma region. That means carbon shifted to gamma position. That means alpha, if you find alpha, that is almost pure iron. And then after ACM line, that means this line, you can find there is gamma Fe3C. And what is written here? After ACM line, carbon percentage decreasing in gamma region. That means here carbon percentage increasing in gamma region, but here carbon percentage is decreasing in gamma region. Then that means carbon percentage is increasing in Fe3C region, because two phases are present in this region. Two phases present, that is gamma and Fe3C. That means gamma, if carbon percent decrease in gamma, that means increase in Fe3C. Simple. And what is the significance of AC1 line? That is the lowest temperature above which austenite can form, because austenite has FCC structure, which is very preferable to reform or deform a body. That is so popular. That's why FCC crystal structure is so important. Now this type question can come in exam. Why maximum carbon content is 6.7%? Why not 10%? Why not 20%? What happen if I add more carbon in iron? What happen? For Fe3C, you can see that is 168 molecular weight, and for carbon this is 12, and overall Fe3C system is 180 and carbon is 12. That means this is a very simple calculation, that is nothing but 6.67%. Okay, and here is the type of steel that I have already told you, that is hypo-eutectoid steel, eutectic steel, and hyper-eutectoid steel. What are these? Means if carbon percent is 0.008% to 0.8%, that means that is eutectic steel, and phase present is ferrite and pearlite. Now what is pearlite? Pearlite means nothing but alpha plus Fe3C. I will explain more after this. And for eutectic steel, 0.8% carbon is present and 100% pearlite is there. And for hyper eutectoid steel, the phase is pearlite and cementite. Pearlite means, again I have told you already, gamma plus Fe3C and cementite. And these are the hyper-eutectoid cast iron and hyper-eutectoid cast iron. Now what are the microstructure? The pearlite. Pearlite means gamma alpha ferrite and cementite is present, but you cannot find alpha ferrite and cementite separately in the microstructure. It is like pearl. Okay, pearl. This is lamellar structure. One white patch, one black patch. One white patch, one black patch. Is like this. Okay, and we can find pearlite below 727 degrees centigrade. Okay, and what is bainite or ladeburite? Bainite or ladeburite, that is gamma austenite plus cementite. Okay, and this structure is plate like structure, and temperature is range is 250 to 550 degrees centigrade. Now, and what is tempered martensite, that will explain in next topic, that is heat treatment. That is martensite, ferrite plus Fe3C. What is martensite? Martensite form when a steel or iron carbon alloy quenched, that means very rapidly cooled. What happened at that time? Carbon cannot diffused from the crystal structure. Then what happened? They will sustain in the crystal structure, but they were not want to stay there. That means the crystal structure is strain hardened. Actually strain hardened, उसका वहाँ पर रहने का मकसद नहीं है, मगर फिर भी रह रहा है क्योंकि it get cooled very fast. It cannot get chance to way out. That's why martensite is so hard sometime in steel structure. This is actually needle shaped grain and the temperature is below 350 degrees centigrade. Now come to the iron carbon phase reaction. There is mainly 4 type of reaction, but I will discuss with you only 3 type of reaction because these are the most important and another one is not so important. Now first one is peritectic reaction. What is peritectic reaction? Here is a part of iron carbon phase diagram. You can see this is the liquid zone, this is the liquid zone, this is liquid plus delta zone, and this is delta zone. And this point, I am considering this point, this point. What happened if I cooled? That means liquid plus delta become gamma. That means one liquid plus one solid becomes another solid, a new solid. That is known as peritectic reaction. Here is the carbon percentage is given. 0.5% carbon is present in liquid and delta ferrite content 0.1% carbon, and we get gamma ferrite, that is known as austenite. This reaction is known as peritectic reaction. Second one is eutectic reaction. What happened? If for 4.3% carbon it occurs, okay, and what happened from liquid we directly get gamma plus Fe3C, gamma plus cementite. This reaction is known as eutectic reaction. Now when you get TIC, no, don't remember, TIC means some liquid will be there. TIC means some liquid will be there always in reaction. Okay, now come to the Eutectoid reaction. Eutectoid reaction is very important and we will concentrate on this reaction mainly. Now what happened for this reaction? We can see that there is a gamma phase and directly convert to alpha ferrite plus cementite. That means one solid become a 2 new solid. Okay, and we are showing the microstructure here for particularly this point. Okay, what happened before this point? We get gamma, means austenite. All these structures are austenite, and suddenly it changed to alpha plus Fe3C. Look, you cannot find out the alpha plus Fe3C. You get, I have told you, pearl-like structure. That's why it is known as pearlite. This is 100% pearlite, a patch of lamellar patch of alpha and Fe3C. Okay, eutectoid reaction can be classified in 2 different way, that is hypoeutectoid and hypereutectoid. This is hypoeutectoid reaction. I have told you at this side is hypoeutectoid, this side is hypoeutectoid and this side is hypereutectoid. Okay, so for this side we are taking few microstructure. You can see there is gamma. At first the microstructure shows the gamma phases and then gradually alpha forms and it gradually increases. These are the alpha patches. Okay, but after a certain temperature it converts to alpha plus Fe3C. That means we form pearlite. We never found alpha and Fe3C separately. These are in form of patch. That's why we get pearlite. We get pearlite and we get alpha. This alpha is known as eutectoid alpha. Okay, now what happened? Okay, so we get alpha plus pearlite. Now what happened in next? That is hypereutectoid reaction. Here for this one alpha was formed because carbon was less, but here you can see Fe3 was formed. Where you get eutectoid alpha, here we get pro-eutectoid Fe3C because this Fe3C patch was formed in this temperature. After that suddenly alpha formed. What happened actually? Here gamma convert to pearlite, and here gamma also converted to pearlite, but as here is carbon was more, that means carbon was directly shifted to Fe3C structures, and they made intermetallic compound, and we get Fe3C more here, but we get less Fe3C here. Okay, so we get pearlite and cementite structure. For hypo-eutectoid reaction, we get alpha plus pearlite reaction. For hyper-eutectic reaction, we get pearlite plus Fe3C structure. Okay. Now some important notes. We have some concept that as 2.14% up to 2.14% is steel, that means 2.14% is used as a steel. No, for maximum use 1.1% carbon is enough. Okay, for steel maximum 1.1% carbon is enough. Even you can remember that for cutting tool we use only 0.8% carbon. Can you imagine how hard it is? Okay, acha. And for railways we use 0.4% carbon. For construction purpose we use 0.2% carbon, which is most softest steel. And for mild steel, this is the range is 0.15 to 0.2%, and 90% of steel is used as mild steel. Now I don't want to explain the tie rule again, because I have already explained in previous lecture. We will solve a tie rule over iron carbon diagram. Now what is the problem? Consider 1 kg of austenite containing 1.15% carbon. Okay, this is given. That means for this diagram we get 1.15% carbon, means this position approx, I am considering this position, this line will be drawn, and below 727 degrees centigrade, that means below this line. Okay, this is 727 degrees centigrade, below this line. That means this point is mentioned in the question. I am drawn this diagram for here to solve the problem. Now we have to solve how many kilogram of each total ferrite and cementite form. कितना ferrite and cementite मिलेगा हमें? This is the question. Now before solve this type of question, you have to know what is the equation. This equation was discussed in tie rule in last lecture. Okay. Now this was the formula you can get. Okay, I am using this diagram. Now we have to know what are the value of C alpha, C0. These are unknown. Okay, so if we consider this 1.15%, this point, and we have to ask ferrite and cementite. Now ferrite, for ferrite, how much carbon can maximum present? That is 0.022%. For cementite it is maximum 6.7%. That means we already know CFE3C and C alpha. Now just we have to put the values here. Weight of alpha percentage means C of Fe3C, percentage of carbon present in Fe3C, given minus given by again carbon percent in Fe3C minus carbon percent is alpha ferrite, nothing else. Same way we can find out the Fe3C percentage. Okay, you can solve this. Now the second part is how many kilograms each pearlite and the pro-eutectoid phase form. Now I have already told you that you cannot get separately alpha and Fe3C. It is impossible. You have to find out the pearlite or ferrite or cementite. You cannot get alpha and Fe3C separately. So the question is how much pearlite can be formed. Now before enter into the problem, we have to know some theoretical parts. Now how much pearlite means, pearlite में कितना carbon होगा, how it is possible to find out. Now come to again to the phase diagram. I have told you the 100% pearlite is formed in this point. That means the 0.76% carbon is present, then it forms 100% pearlite. That means pearlite contains 0.76% carbon. Okay, 0.76% carbon. And for already we know for AP3C maximum carbon percent is 6.7%, and for carbon alloy, for carbon present in the given point is 1.15%. So we can easily calculate the weight of pearlite. Means again according to tie rule, that is carbon percent present in Fe3C minus given by again carbon percent present in Fe3C by minus carbon present in pearlite. Same way we can find out the Fe3C and we get this both one. Now we have to study the hardness. That is the one of the property of different phases. It is already given that α-Ferrite has 70 Brinell hardness number and cementite has 700 Brinell hardness number. Now more the Brinell hardness, more the harder material. It shows that the presence of cementite is caused of ductility, brittleness or hardness in the steel or cast iron, and α-Ferrite is actually the soft material and hardness is very cementite is very hard material. Now which type of crystal structure is easy to deform for a metal? It is already given that in room temperature FCC is easy to deform, but we already get in iron carbon diagram that austenite or gamma ferrite is FCC and alpha ferrite is BCC. Now if we want to deform iron very easily and it is cooled normally, that means the iron is BCC, and which is deformable in high temperature, not in room temperature. And if we apply some heat, it converts to gamma ferrite, which is FCC, and this is deformable in room temperature. This is the biggest problem and biggest what we can say the gift of nature. That's why iron is used in maximum amount of use of iron in our today's civilization. Now what we have to do, we have to hold this gamma or austenite structure in room temperature. That's why heat treatment is needed, which will be discussed in next video. Thank you.